A fleck of paint, smaller than a grain of rice, spins above your head at 17,000 miles per hour. It isn't glowing. It isn't even visible. But in the silence of orbit, it hits a satellite, and the satellite ceases to exist. No explosion, no sound, just impact and disappearance. Somewhere below, your GPS flickers. A weather forecast goes dark. A cargo ship loses its navigation mid-ocean. You don't notice. You won't. Because when machines die in orbit, they die in silence. We imagine space as infinite, an ocean of emptiness. It isn't. It's a crowded hallway, and every object inside is moving faster than a bullet. A single collision can turn aluminum into vapor, solar panels into shrapnel, and communication into chaos. The first piece of space junk still floats up there. Vanguard 1. Launched in 1958, it stopped talking to Earth 6 decades ago, but it still circles the planet every 100 minutes, a silent relic of when space meant hope. We built Progress into orbit and never went back to clean it. Now, every mission adds a new fragment. Shards of rockets, splinters of paint, the lost wrench from an astronaut's glove. Together, they form an invisible cloud that wraps around our planet like a curse of our own making. That paint fleck isn't alone. It has 100 million siblings, and they're all moving. If each fragment were a grain of sand, you could fill an Olympic pool. Except this sand travels at speeds that turn metal to vapor and satellites to ghosts. We didn't design orbit to be dangerous. We just stopped designing it all. The glove was lost in 1965, a Russian cosmonaut's tool, tumbling away during a spacewalk. 60 years later, it's still up there, moving fast enough to punch through steel. Low Earth orbit hosts fragments from decades of missions. Solar panels, rocket nose cones, splintered antennas, even flecks of paint smaller than your fingernail. Together, they form a cloud engineers call a debris belt. One collision produces thousands more hazards. Engineers scramble to recalculate satellite trajectories, but the fragments are already elsewhere, an invisible shuffle in three-dimensional space. Imagine a highway where every car moves at impossible speed, but in different directions. You can't slow down. You can't swerve. You can only calculate and hope you're not in someone else's lane. Engineers track fragments larger than 10 centimeters, roughly the size of an orange. Everything smaller is invisible. That's 95% of debris. Untracked, unrelenting, unavoidable. Satellites can maneuver, but each course correction burns fuel they cannot replace. Dodge too often, and you shorten a satellite's operational life by years, trading immediate survival for early death. And yet humans keep launching. Each new satellite adds a few dozen fragments. Each collision multiplies them exponentially. Collisions don't eliminate debris. They increase it. Right now, above your head, this cloud circles silently. It doesn't pause for borders, treaties, or human hope. It just moves and waits for the next impact. In 2009, 2 dead satellites collided over Siberia. There was no fireball, no visible explosion, just 2 objects that stopped existing as satellites and started existing as thousands of threats. The collision proved every engineer's nightmare. In orbit, one mistake doesn't end. It multiplies. The question became, how many collisions until orbit becomes unusable? Engineers call it the critical density threshold, the point in orbit where debris multiplies faster than it can be tracked. Once reached, collisions become inevitable, even if humans stop launching entirely. That's Kessler Syndrome, orbit cleaning itself through destruction or becoming permanently unusable. In 2009, it happened silently. 2 dead satellites, the Iridium-33 and Cosmos 2251, collided. From just those 2 objects, 2,000 trackable fragments emerged. Countless smaller flecks, too tiny for radar, scattered across low Earth orbit. Each fragment becomes a hazard. Each collision spawns hundreds more. The cascade doesn't announce itself. It appears gradually, then suddenly, then irreversibly. At orbital velocities, kinetic energy transforms even a paint fleck into a weapon. Aluminum panels vaporize. Carbon fiber shatters. Electronics die instantly. One impact isn't contained. It multiplies across orbital zones. Computer models project patterns decades ahead. One collision this decade could trigger 5 the next, 25 the decade after. Exponential growth doesn't negotiate. It happens. Satellites maneuver to avoid debris, but each course correction burns fuel they can't replace. Dodge too often, and a satellite's operational life shortens by years, trading immediate survival for early death. The smallest fragments, pennies, paint chips, bowl fragments, escape all tracking. They're 95% of what's up there, silently threatening everything above us. Now, imagine you're the engineer approving the next launch. You know the cascade is accelerating. Every satellite you send could survive, or become the catalyst for hundreds more hazards. One decision, and the orbit you depend on might multiply danger instead of reducing it. The question isn't if the cascade will happen. It's which satellites become unreachable first. Your GPS blinded, weather monitors destroyed, communication satellite silenced. October 2022 offered a stark warning. A Starlink satellite received 25 collision alerts in a single day. Not glitches, real, tracked threats from NORAD. 6 emergency maneuvers burned 40% of its maneuvering fuel designed to last a decade. Engineers had exhausted contingency reserves in a single day, leaving the satellite vulnerable for its remaining operational life. The stakes extend far beyond navigation apps. Banking networks rely on satellite timestamps to reconcile transactions across continents. Precision agriculture uses GPS to guide autonomous tractors within centimeters. Aviation depends on satellite positioning for every takeoff and landing. These systems aren't backups, they're primary infrastructure. A failure isn't inconvenient, it's systemic. Economic costs compound rapidly. Each avoidance maneuver consumes fuel, shortens mission lifespans, and increases insurance premiums. Satellite constellations delay deployments by months. The James Webb Space Telescope postponed critical mirror adjustments 3 times in 2023 due to debris proximity. Innovation waits while operators calculate risk. Orbital debris doesn't distribute evenly. Ground-based radar has blind zones, regions obscured by Earth's curvature, where satellites fly blind for hours through the most congested paths. In these corridors, one minor collision can initiate a cascade, altering trajectories unpredictably, forcing more maneuvers, creating more risk, a feedback loop of exponential growth. Mathematical models warn of thresholds. The Iridium-Cosmos collision left debris that will persist for decades. Simulations show that just 5 more collisions of similar magnitude could render specific low Earth orbit bands statistically unusable. Critical satellites could become unreachable. Astronauts could be stranded in orbit, supply missions delayed or impossible. The consequences are human, immediate, and measurable. Over 8,000 active satellites now circle Earth, triple the number from 2019, alongside 3,000 defunct satellites and countless spent rocket stages. Each launch adds potential multipliers. The question isn't whether the cascade will continue. It's which infrastructures fail first, and whether we'll notice before it's too late. Space agencies have attempted orbital debris removal, but the physics and economics resist simple solutions. ESAs remove debris-tested nets and harpoons on small fragments. Japan explored magnetic tethers to drag debris into lower orbits. ClearSpace. One plans to grapple a single defunct satellite. Each mission is painstakingly precise, yet the debris cloud outnumbers removal capacity by orders of magnitude. Physical cleanup cannot match the scale. Fragments travel at orbital velocities. Any misstep risks creating more hazards. Costs per target reach hundreds of millions, limiting action to a fraction of the problem. A single grain sifted from a desert. Secondary challenges compound the difficulty. Who pays? Whose debris? Who authorizes action in international space, where no single nation has jurisdiction? Legal ambiguity and competing priorities slow consensus. Prevention outpaces cure. Satellites are now designed to deorbit autonomously or permit in-orbit servicing, but adoption is uneven. Some operators still prioritize launch schedules over stewardship. Each cleanup removes individual threats while the overall population grows. The rate of creation exceeds the pace of removal, and the gap widens yearly. Political and financial deadlocks make every mission a negotiation rather than a solution. Even with technology and funding, the problem cannot be fully eliminated. Humanity is learning the limits of intervention. Mitigation is possible. Victory is not. The orbital environment becomes an intricate network of interdependent risks, each decision weighted, each fragment consequential. Orbit, once an empty frontier, is now threaded with imperceptible hazards. Debris from decades of exploration drifts unpredictably, set to linger for decades or centuries. Some fragments will remain 50, 100, 200 years, far beyond the lifespan of their creators. Will humans still be launching satellites then, adding new debris to the inherited cloud? The paradox extends to Mars. Future missions, rovers, orbiters, satellites, will leave similar trails around other planets. Expansion exports the problem. Tomorrow's explorers inherit yesterday's mistakes. Cleanup technologies offer partial solutions, but cannot match the scale. Prevention works only if universally adopted. Yet international coordination lags, funding is limited, and ambition presses onward. Every decision today shapes environments that future generations will encounter. The irony is stark. We reach for the stars, only to entangle ourselves in a problem we cannot fully solve. Risks persist long after human oversight fades. The final tension isn't technical. It is temporal and ethical. Will we learn from these mistakes, or merely repeat them elsewhere? One planet at a time, one orbit at a time? The question remains unresolved, and the answers will unfold decade from now, orbit by orbit, decision by decision.